Hello, my name is Hainer Betancourt.
My name is Taylor Lakin.
And my name is Nabil Twyman.
And we are here to explain this phenomenon. Okay, so today we'll be explaining to you why the car stays at a relative position and does not move with the truck. As you can see in the beginning, both the car and the truck are at rest. Once the truck begins to move, the back of the car falls first and then the front. And don't worry, we'll be explaining this, we'll be breaking it down, and we'll simplify it as much as we can. But yeah, most thing you have to watch when you look at this GIF is that the car does not move with the truck. Rather, it just drops down from the back and then to the front, and it just stays in that same position.
So, in the very beginning, both the truck and the car are at rest. So, imagine two blocks stacked one above another. One will represent the truck, while the other represents the car that was on it.
Each of the forces that both of the objects experience cancel each other out. The car experiences its own weight, its force of gravity, and the normal force, or the force that supports the car from the top of the truck. Meanwhile, the truck experiences both its own weight and the weight of the car, both forces of gravity, and is supported by a normal force which comes from the ground beneath it.
This eventually shows when the truck starts to move, there's a change in velocity, which is acceleration. And that acceleration, it's towards the left, which is where the truck is moving towards.
While the truck is accelerating to the left, relative to the truck, the car seems to accelerate to the right.
Due to Newton's second law, which states that an unbalanced force applied to an object causes it to accelerate, the acceleration must be caused by a force going in that direction.
Because the truck and the car are not completely connected, the only thing that could balance the forces is static friction, which prevents one object from moving at a different velocity than the surface it is against. However, based on the surfaces involved and the amount of force applied perpendicular to them, there will be a maximum magnitude of static friction that a strong enough force can overcome.
So what we see on the slide is a real-life model. And Nabil's going to end up pushing that book, and when he pushes the book, the block itself remains in the same position it's at.
In short, the magnitude of acceleration from the truck creates an applied force that overcomes the static force between the two. Once the part of the car is in the air, it loses the normal force that keeps it up, and thus falls to the ground.
Congratulations! We figured out how it works.
Actually, kind of.
We made one assumption that kind of changes the explanation.
We assumed that the wheels weren't moving, but now we're going to try to figure this out if the wheel was moving. So it seems the same because the car is still placed on the truck, so the magnitude of any force applied to the truck has to overcome the static force between the two bodies to keep the car from moving. Except it doesn't have to. In fact, it would take less force to reach the same result.
Well, you may ask why may that be. Well, when a force is applied to the truck, the sudden motion of the truck, the bottom of the wheels always stay with the truck due to the friction between them. The force being applied is not strong enough to overcome the static friction. Instead, the force overcomes the static friction between the wheel axle and the rest of the car.
In this model, we clearly see the wheels of the car going in an opposite direction than the book, which we can assume is the truck. This shows how easily it is able to remain in its place, because once it makes contact with the ground, the static friction is greater than the force applied to the surface, which is minimal. This clearly shows an opposite movement of the wheels.
What we see here is a diagram of a car axle. as we keep in mind, the car axle is what overcomes static friction in order to create the movement on the wheel, making the car, move where it is. So it's very hard to explain where specifically the movement comes from, since the axle is a very complex system in the cars. So all you really would have to know is just that this car is not being accelerated by itself. It's just in place. It's in neutral, and what happens to that is, since there's nothing to stop the axle from turning itself, it will do it since it can overcome static friction very easily.
So, can this be prevented? It's not very hard to figure it out. As we first assumed that the wheels were moving, the car fell off with less force necessary to move it due to the ability of the axles in the car to overcome friction because of the lubrication used in order to allow vehicles to move.
Therefore, if we were to lock the wheels, but by either using the brakes or putting on a parking brake, then the wheels won't be able to turn, which is what caused the car to stay in place in the first place.
So in this model, the wheels of the car are locked in place. It took a greater force for the car to fall off the book, which we assume it's the truck. So once the book is pushed, from underneath the car, the wheels don't rotate since they're in a locked position. They're taped. And in this model, we can see that an inaccuracy as the wheels in the car are plastic, but theoretically, if they were rubber, they would have moved with the truck. They would have not stayed in that same position, since a greater force would be necessary to bring the car off of the truck. And it would have either fallen off later if the truck were to accelerate, and that acceleration would cause the coefficient of static friction to be overcome, or it would just have remained on top of the truck.
Alternatively, if the truck were to take off with less speed than it did in the video, then perhaps it could create a force that is weaker than the one prior, which could not be able to counteract the static friction between the two bodies.
Thank you for
watching.
And we hope that you understood what caused this phenomenon.
Bye-bye.